Tonight, as you settle into the comfort of darkness, I want you to imagine something extraordinary. Picture yourself floating in the infinite black of space, surrounded by a gentle river of light that stretches across the entire cosmos. This isn't just any river. This is our home, the Milky Way galaxy. And tonight we're going to embark on the most incredible journey you could ever imagine. A journey to the very heart of our galactic home. If you find solace in these gentle explorations of the cosmos, I'd be deeply grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deeply, and let your imagination carry you through the star-filled darkness. Also, I'd love to know where you're listening from tonight. Comment your time and location below. There's something profoundly beautiful about contemplating our galactic journey while scattered across our small planet, all of us under the same ancient sky. What we're about to explore together will challenge everything you think you know about scale, time, and our place in the universe. We're going to travel from the quiet suburbs of our solar system, through bustling stellar neighborhoods, past regions where stars are born and die in spectacular fashion, until we reach the most mysterious and powerful place in our entire galaxy, the supermassive black hole that anchors everything we call home. This journey spans not just incredible distances, but incredible mysteries. We'll discover why our galaxy has the shape it does, how spiral arms maintain their elegant curves across hundreds of millions of years, and what forces sculpt the cosmic architecture that surrounds us. We'll encounter stellar nurseries where new suns ignite, ancient globular clusters that remember the galaxy's youth, and regions so dense with stars that night would never truly fall. But perhaps most remarkably, we'll come to understand that this journey isn't just about exploring space, it's about exploring time itself. Because when we look toward the galactic center, we're peering through layers of cosmic history, witnessing events that shape not just our galaxy, but the very elements that make up our bodies. So let's begin this gentle descent into one of the most magnificent structures in the known universe. Let's travel together to the center of the Milky Way. Our journey begins exactly where you are. Right now, Earth orbiting our familiar yellow sun located in what astronomers call the local bubble. We're not in some random corner of the galaxy. We're positioned in a very specific neighborhood, about 26,000 light-years from the galactic center. To put this in perspective, if our entire galaxy were the size of the United States, we'd be living somewhere around Kansas City. Not quite the center, not quite the edge, but in a comfortable suburban region where stars are spaced at reasonable distances and the cosmic weather is generally mild. This location isn't an accident. We exist here because this region of the galaxy offers something precious: stability. The Milky Way is a dynamic, ever-changing system where stellar explosions, gravitational waves, and intense radiation can make large regions uninhabitable. But here, in what scientists call the galactic habitable zone, conditions have remained steady enough for billions of years that complex chemistry could evolve into life. From our vantage point, the galaxy appears as that familiar band of light stretching across our night sky. Ancient cultures saw this river of stars and called it many names. The Greeks called it the Milky Way, from their word galaxius, meaning milky. The Romans knew it as Via Lacta. Indigenous peoples around the world saw it as a pathway for spirits, a cosmic river, or the backbone of night itself. They were all describing the same magnificent structure we're about to explore from the inside. But what exactly are we looking at when we gaze up at that band of light? We're seeing our galaxy edge on, like looking at a dinner plate from the side. The Milky Way is what astronomers call a barred spiral galaxy, roughly 100,000 light-years in diameter, and containing between 200 and 400 billion stars. That's more stars than there are grains of sand on all the beaches of Earth, all held together by gravity in an elegant cosmic dance that's been ongoing for over 13 billion years. The structure we're embedded within isn't random. Our galaxy has a distinct architecture, like a cosmic city with different neighborhoods, each with its own character and population. There's the thin disk where we live, populated by younger stars, gas and dust. There's the thick disk above and below us, home to older stellar populations. Surrounding everything is the galactic halo, a roughly spherical region containing the galaxy's most ancient stars arranged in beautiful globular clusters that orbit like satellites around the main galactic structure. And threading through it all are the spiral arms. These aren't fixed structures like the spokes of a wheel, but rather density waves that sweep around the galaxy, compressing gas and triggering star formation as they pass. It's like a cosmic traffic pattern that creates the beautiful spiral structure we observe in other galaxies and exist within ourselves. As we prepare to leave our comfortable neighborhood and venture inward, it's worth appreciating just how perfectly positioned we are to observe the universe. We're far enough from the galactic center to avoid the intense radiation and gravitational chaos found there, but close enough to the galactic plane to witness the full glory of stellar evolution. We're in a region where heavy elements, forged in previous generations of stars, have enriched the local environment, making rocky planets and complex chemistry possible. Our Sun orbits the galactic center roughly once every 225 million years. This is called a galactic year, and Earth has completed about 20 of these cosmic orbits since complex life first emerged in our oceans. During our last galactic year, dinosaurs ruled the Earth. The next time we complete this orbit, our Sun will be noticeably older, and if humans still exist, they will have witnessed cosmic changes we can barely imagine. But tonight, we're not content to simply orbit. We're going to travel inward through regions of space where the stellar density increases, where the gravitational forces grow stronger, and where the very nature of space and time begins to behave in ways that challenge our everyday understanding. The first part of our journey takes us through what astronomers call the local arm, or sometimes the Orion arm. This is the spiral arm segment where our solar system currently resides. It's a relatively minor arm compared to the galaxy's grand design, more of a spur connecting the larger Perseus and Sagittarius arms. But minor doesn't mean insignificant. This region contains some of the most beautiful and scientifically important objects in our local galactic neighborhood. As we travel inward from our solar system, we encounter the diverse stellar population that makes up our local environment. Within just a few dozen light-years of Earth, we find red dwarfs that will burn for trillions of years, massive blue giants that live fast and die young, and white dwarf stars that represent the final fate of stars like our Sun. Each of these stellar types tells us something about the life cycle of matter in our galaxy and the processes that have been shaping cosmic evolution for billions of years. One of the most striking features we encounter as we move inward is the Gould Belt, a ring of young, hot stars and star-forming regions that surrounds our solar system. This structure, named after astronomer Benjamin Gould, who first mapped it in the 1870s, represents a relatively recent burst of star formation in our galactic neighborhood. The belt is tilted about 20° relative to the galactic plane and contains many of the bright stars and nebulae visible to the naked eye from Earth. Within the Gould Belt, we find stellar nurseries where new stars are being born right now. The Orion Nebula, visible as the sword in the constellation Orion, is perhaps the most famous of these cosmic maternity wards. Here, dense clouds of gas and dust are collapsing under their own gravity, heating up as they contract until they reach the critical temperature needed to ignite nuclear fusion. It's a process that transforms simple hydrogen into the energy source that powers stars for billions of years. But star formation isn't a gentle process. It's violent, chaotic, and beautiful. As massive stars form, they emit intense stellar winds that blow away surrounding material, creating cavities in the interstellar medium. When these massive stars reach the end of their lives, they explode as supernovae, sending shockwaves through space that can trigger new rounds of star formation, while simultaneously enriching the local environment with heavy elements forged in their cores. These stellar explosions have shaped our local galactic environment in profound ways. We exist within what's called the local bubble, a region of space that's been swept relatively clean of dust and gas by ancient supernova explosions. This bubble extends for several hundred light-years in all directions and gives us a clear view of the cosmos beyond. Without this clearing, our night sky would be much dustier, and our ability to study distant galaxies would be severely limited. As we continue our journey inward, the stellar density begins to increase. What started as a leisurely cruise through the galactic suburbs gradually becomes a journey through more crowded stellar neighborhoods. The average distance between stars decreases from the 4.3 light-years that separate us from our nearest stellar neighbor, Alpha Centauri, to distances measured in single light-years or even less. This increasing stellar density has profound implications for planetary systems and the potential for life. In regions where stars are closely packed, gravitational interactions become more common. Planetary orbits that would be stable for billions of years in our quiet neighborhood might be disrupted by passing stars in these denser regions. Close stellar encounters could strip planets from their host stars, or send comets and asteroids careening through interplanetary systems. But the increasing density also brings opportunities. The probability of observing spectacular astronomical events increases dramatically. Stellar collisions, though still rare, become possible. Binary star systems, where two stars orbit each other in an intricate gravitational dance, become more common, and the sheer variety of stellar types and evolutionary stages creates a cosmic laboratory where we can observe phenomena that simply don't occur in our local neighborhood. One of the most remarkable aspects of our inward journey is how the interstellar medium begins to change. The space between stars, which we often think of as empty, is actually filled with gas, dust, magnetic fields, and various forms of radiation. In our local neighborhood, this material is relatively sparse, cleared out by ancient stellar explosions. But as we move toward the galactic center, the density of this interstellar material increases dramatically. The dust isn't just cosmic debris, it's the raw material from which new stars and planets form. These tiny grains, typically smaller than the particles in cigarette smoke, are forged in the atmospheres of dying stars and scattered throughout the galaxy by stellar winds and supernova explosions. Each grain carries within it the chemical history of previous generations of stars, including the carbon, oxygen, silicon, and iron that will eventually become incorporated into new worlds. The magnetic fields threading through this material create structure and influence how gas flows through the galaxy. These fields, though incredibly weak by terrestrial standards, extend across vast distances and help channel material into the spiral arms where it can participate in new rounds of star formation. They also accelerate charged particles to incredible energies, creating the cosmic rays that constantly bombard our solar system and every other star system in the galaxy. As we penetrate deeper into the Milky Way structure, we begin to encounter the galaxy's spiral arms themselves. These aren't fixed features, but rather waves of density that sweep around the galactic disk, compressing material as they pass and triggering the formation of new stars. The spiral pattern we see in other galaxies and that we're now experiencing from within is maintained by a delicate balance of gravitational forces and rotational dynamics that astronomers are still working to fully understand. The spiral arms represent some of the most active and dynamic regions of the galaxy. Here, the interstellar medium is compressed to densities high enough that gravity can overcome the thermal pressure of gas clouds, triggering collapse and star formation. The newly formed massive stars illuminate their surroundings with intense ultraviolet radiation, creating the beautiful emission nebulae that trace out the spiral pattern in photographs of other galaxies. But these regions of active star formation are also regions of stellar death. The most massive stars burn through their nuclear fuel in just a few million years before exploding as supernovae. These explosions inject enormous amounts of energy into their surroundings, heating the interstellar medium, accelerating cosmic rays, and triggering shockwaves that can either promote or inhibit further star formation depending on the local conditions. The interplay between stellar birth and death in the spiral arms creates a complex ecosystem of matter and energy. Material is constantly being cycled between the interstellar medium and stellar interiors, with each cycle adding new heavy elements to the galactic chemical inventory. This process, known as galactic chemical evolution, has been operating for over 13 billion years and is responsible for creating the rich variety of elements that make rocky planets and complex chemistry possible. As our journey continues, we'll encounter even more extreme environments, regions where the normal rules of stellar physics are stretched to their limits, and ultimately the mysterious heart of our galaxy, where space and time themselves become warped by the presence of a supermassive black hole containing the mass of 4 million suns. But that's a destination that requires careful preparation and understanding. For now, let's pause and appreciate where we are in this cosmic journey, traveling through the spiral arms of our galaxy, witnessing the ongoing cycle of stellar birth and death that has been shaping our cosmic home since the universe was young. The adventure has only just begun, and ahead of us lie wonders that will challenge our understanding of physics, astronomy, and our place in the cosmic order. The deeper we venture into our galaxy's spiral arms, the more we begin to encounter something truly extraordinary. The Perseus arm, one of the Milky Way's major spiral features, stretches before us like a cosmic highway paved with newborn stars and glowing nebulae. Here, the interstellar medium becomes denser, richer, more alive with the raw materials of creation. Imagine floating through a region where star formation occurs not as isolated events, but as grand collaborative efforts spanning hundreds of light years. Massive molecular clouds, some containing the mass of 1 million suns, drift through space like cosmic icebergs. Within these clouds, temperatures drop to just a few degrees above absolute zero, creating conditions so cold that molecules freeze onto dust grains, building up icy mantles of water, methane, and ammonia. These molecular clouds represent some of the most pristine material in the galaxy, gas that has been enriched by countless generations of stellar death and rebirth, now gathered into dense concentrations where gravity can begin its patient work of building new worlds. The process isn't hurried. It can take millions of years for a molecular cloud to contract enough for star formation to begin, but when it does, the results are spectacular. As we drift through the Perseus arm, we encounter star-forming complexes that dwarf anything in our local neighborhood. The Cygnus X region, one of the most active stellar nurseries in our part of the galaxy, stretches across nearly 600 light-years and contains enough material to form several million stars like our Sun. Here, the night sky would be ablaze with the light of young hot stars and the colorful glow of ionized gas clouds stretching in all directions. But it's not just the scale that's impressive, it's the organization. The spiral arms aren't random collections of stars and gas, but carefully orchestrated regions where density waves compress material in predictable patterns. As these waves sweep around the galaxy at a different speed than the stars themselves, they create a kind of cosmic traffic jam, where material piles up, becomes compressed, and eventually reaches the critical density needed for gravitational collapse. This process creates what astronomers call stellar associations, loose groupings of young stars that formed from the same molecular cloud and are now slowly drifting apart. As they orbit the galactic center, these associations tell the story of recent star formation, like cosmic archaeology written in the positions and motions of stellar siblings born from the same celestial nursery. As our journey carries us through these bustling stellar neighborhoods, we begin to notice something remarkable about the chemistry of space itself. The interstellar medium here is enriched with elements that simply didn't exist when the galaxy was young. Oxygen, carbon, nitrogen, silicon, iron, and dozens of other elements are mixed into the gas and dust, the products of stellar nucleosynthesis from previous generations of stars. This chemical enrichment represents one of the most important processes in cosmic evolution. When the universe was young, it contained only hydrogen and helium, with trace amounts of lithium. Everything else, every element heavier than helium that makes up the rocky planets, the molecules of life in our own bodies, was forged in stellar cores and scattered through space by stellar winds and supernova explosions. The spiral arms serve as both the factories and the distribution centers for this cosmic chemical evolution. Here, massive stars live their brief but brilliant lives, fusing lighter elements into heavier ones in their cores. When these stars explode, they don't just release energy, they release the periodic table itself, sending newly forged elements racing through space at thousands of kilometers per second. These supernova shock waves do more than just distribute heavy elements. They also compress the surrounding interstellar medium, triggering new rounds of star formation. It's a self-perpetuating cycle, where stellar death enables stellar birth, and each generation of stars is slightly more metal-rich than the last. Astronomers call this process galactic chemical evolution, and it's been operating in the spiral arms for over 10 billion years. But the spiral arms aren't permanent features. They rotate around the galactic center at a different rate than the stars themselves, creating a pattern that persists even as individual stars and gas clouds move in and out of the spiral structure. Our own solar system has passed through several spiral arms during its 4.6 billion year history, experiencing periods of enhanced stellar formation and increased supernova activity as it did so. Some scientists believe these passages through spiral arms may have influenced the evolution of life on Earth. The increased cosmic ray flux from nearby supernova explosions could have caused genetic mutations, potentially accelerating evolutionary change. The enhanced star formation could have created more massive stars in our neighborhood, leading to spectacular supernova displays that would have been visible in Earth's ancient skies. As we continue our inward journey, the stellar population around us begins to change in subtle but important ways. The stars become, on average, more massive and more luminous. The proportion of binary and multiple star systems increases, and we begin to encounter stellar types that are rare or absent in our quiet galactic suburb. Wolf-Rayet 8 stars, for example, represent one of the most extreme phases of stellar evolution. These objects have stripped away their outer hydrogen layers, exposing their helium-burning cores to space. They shine with the luminosity of hundreds of thousands of suns and drive stellar winds so powerful they can clear cavities dozens of light-years across in the surrounding interstellar medium. These are stars living on borrowed time, racing through their nuclear fuel reserves before ending their lives in some of the most energetic explosions in the universe. The presence of these exotic stellar types creates a more dynamic and dangerous galactic environment. The intense ultraviolet radiation from massive stars can sterilize planetary surfaces across interstellar distances. The stellar winds and supernova shockwaves can strip away planetary atmospheres or trigger massive climate changes on worlds orbiting nearby. Yet this same harsh environment is also incredibly fertile for the creation of complex chemistry. The intense radiation fields break apart molecules and atoms, creating ions and free radicals that can participate in chemical reactions impossible under the gentler conditions of our local neighborhood. The shock waves from stellar explosions compress and heat interstellar material, driving chemical reactions that create some of the most complex molecules known in space. Astronomers have detected over 200 different molecular species in the interstellar medium, ranging from simple two-atom molecules like carbon monoxide to complex organic compounds containing dozens of atoms. Some of these molecules, like glycine and other amino acids, are the basic building blocks of life as we know it. Their presence in star-forming regions suggests that the chemistry of life may be a natural consequence of the physical and chemical processes operating in galactic spiral arms. As we penetrate deeper into the galaxy's structure, we also begin to encounter the effects of the galactic magnetic field. This field, though incredibly weak by terrestrial standards, extends throughout the galaxy and plays a crucial role in channeling the flow of gas and cosmic rays. The field lines tend to align with the spiral arms, creating magnetic highways that can funnel material toward the galactic center or channel it into regions where star formation is favored. The magnetic field also accelerates charged particles to incredible energies, creating the cosmic rays that permeate the galaxy. These high-energy particles, primarily protons and atomic nuclei, race through space at nearly the speed of light, carrying energy from stellar explosions and active galactic nuclei to every corner of the Milky Way. When they interact with interstellar gas and dust, they create secondary particles and gamma rays that allow astronomers to study regions of the galaxy that are otherwise hidden by dust. But perhaps most remarkably, as we journey deeper into the galaxy, we begin to sense something that's been pulling at us all along, a gravitational presence so massive and so concentrated that it warps the very fabric of space-time around it. Even from thousands of light-years away, we can feel its influence in the orbital motions of stars, in the flow patterns of interstellar gas, and in the overall architecture of the galactic disk. This is our destination, the galactic center, home to Sagittarius A, a supermassive black hole containing the mass of over 4 million suns compressed into a region smaller than the orbit of Mercury. It's a place where the normal rules of physics are stretched to their absolute limits, where time itself runs slower than in our comfortable galactic suburbs, and where matter spirals inward at velocities approaching the speed of light, before vanishing forever beyond the event horizon. But reaching this destination will require us to traverse some of the most extreme environments in the galaxy, regions where stellar densities are thousands of times higher than in our local neighborhood, where massive stars are packed so closely together that their gravitational interactions create a constantly changing stellar dance, and where the interstellar medium is heated to temperatures of millions of degrees by the collective energy output of countless massive stars. The journey ahead will take us through the galactic bulge, that central concentration of ancient stars that forms the heart of our galaxy. We'll encounter globular clusters, those spherical cities of stars that have orbited the galactic center for over 10 billion years, preserving within their stellar populations the chemical signature of the galaxy's youth, and will witness phenomena that occur nowhere else in the cosmos. From hypervelocity stars ejected from the galactic center at thousands of kilometers per second, to streams of gas falling inward to feed the central black hole. As we prepare for the next phase of our journey, it's worth pausing to appreciate how far we've already traveled. We've left behind the quiet stellar suburbs where we were born and ventured into the bustling metropolitan regions of our galaxy. We've witnessed star formation on industrial scales, encountered stellar types that exist nowhere in our local neighborhood, and observed the ongoing chemical evolution that has been enriching the galaxy for billions of years. But ahead of us lies an even more remarkable adventure, a journey into the very heart of our cosmic home, where gravity reigns supreme, and the mysteries of black holes, dark matter, and the fundamental nature of space-time await our exploration. The center of the Milky Way is calling, and we're about to answer that cosmic invitation with wonder, curiosity, and the gentle determination that drives all great explorations. The next phase of our journey will challenge everything we think we know about the universe and our place within it. As we prepare to leave the familiar spiral arms behind, something profound begins to shift in the cosmic landscape around us. The gentle stellar neighborhoods we've grown accustomed to start giving way to something far more ancient, far more densely packed, and infinitely more mysterious. We're approaching the galactic bulge, that central swelling of our galaxy, where 10 billion years of cosmic history have compressed into a region that defies everything we thought we knew about stellar populations. The transition isn't sudden. It's like watching a suburban landscape gradually transform into a dense urban core. The spaces between stars, which once measured in light years, now shrink to distances that would fit comfortably within our own solar system. Where we once encountered perhaps one star every few cubic light years, we now find ourselves surrounded by stellar densities that would make our night sky blindingly bright if we could somehow transport Earth to these regions. But it's not just the density that changes. The very nature of the stars around us tells a story of cosmic archaeology. These are the galaxy's senior citizens, ancient red giants and evolved stars that formed when the Milky Way was young and the universe contained far fewer heavy elements. Their reddish glow speaks of ages measured in billions of years, of stellar lives that began when the first complex galaxies were still taking shape across the cosmos. Here in the galactic bulge, we encounter stellar populations that astronomers classify as population 2 stars. Unlike the metal-rich warm stars of the spiral arms, these ancient suns formed from gas that had been enriched by only the first few generations of stellar death and rebirth. Their atmospheres contain less iron, fewer heavy elements, and their light carries the chemical signature of a younger, simpler universe. The architecture of space itself becomes more complex as we penetrate deeper into this region. The orderly spiral structure that guided our journey thus far begins to dissolve into something more chaotic, more three-dimensional. Stars move in elliptical orbits that carry them high above and below the galactic plane, creating a roughly spherical distribution that extends thousands of light years in all directions from the galactic center. This isn't random motion. These orbital patterns were sculpted by billions of years of gravitational interactions, by the slow but inexorable influence of the central black hole, and by the complex dance between dark matter and ordinary matter that shapes the deepest architecture of our galaxy. Each star follows a gravitational choreography that was set in motion when the galaxy was young, and their collective motion creates the bulging elliptical structure that dominates the inner regions of the Milky Way. As we drift deeper into this ancient stellar realm, we begin to encounter some of the most remarkable objects in our galaxy. Globular clusters, those perfect spheres of stars that shine like cosmic jewels, become more common. Each cluster contains hundreds of thousands of stars packed into a region just a few dozen light-years across, creating stellar densities so extreme that the night sky from within such a cluster would contain thousands of stars brighter than Venus appears from Earth. These globular clusters are time capsules, preserving within their stellar populations the conditions that existed when the galaxy was young. The stars within them form nearly simultaneously from the same primordial gas cloud, and they've been orbiting together ever since, slowly evolving but maintaining their gravitational cohesion across cosmic time. By studying their color, brightness, and chemical composition, astronomers can read the story of the early universe written in starlight. But globular clusters reveal something else as well, something that challenges our understanding of how galaxies form and evolve. Many of these clusters show evidence of multiple stellar populations, suggesting that star formation within them occurred in several distinct episodes. Some clusters contain stars with different chemical compositions, different ages, and different evolutionary histories, all somehow bound together in the same gravitational embrace. This complexity hints at the violent history that shaped the galactic bulge, rather than forming through a single gradual process. The central regions of our galaxy appear to have been assembled through multiple episodes of stellar formation, galactic collisions, and the accretion of smaller satellite galaxies. Each merger event would have stirred the stellar populations, mixed different chemical signatures, and contributed to the complex orbital structure we observe today. The evidence for this violent past becomes more apparent as we examine the motions of stars around us. Unlike the orderly rotation of the galactic disk, stars in the bulge move in chaotic, highly elliptical orbits that carry them on complex, three-dimensional paths around the galactic center. Some stars dive deep toward the central black hole before swinging back out to the edge of the bulge. Others follow box-like orbits that never take them close to the galactic plane. These orbital patterns preserve the memory of ancient gravitational encounters. When two galaxies collide and merge, their stellar populations don't simply blend together smoothly. Instead, gravitational forces stretch and distort the original orbital structure, creating the kind of complex three-dimensional stellar distribution we observe in the galactic bulge. The stars we see around us are the surviving remnants of these ancient cosmic catastrophes. But the bulge isn't just a graveyard of ancient stellar populations. It's also a region of ongoing activity, where the intense gravitational environment creates phenomena that occur nowhere else in the galaxy. The high stellar densities lead to frequent close encounters between stars, sometimes resulting in stellar collisions or the formation of exotic binary systems where two stars orbit each other at distances closer than the diameter of our Sun. These close stellar encounters can have dramatic consequences. When two main sequence stars collide, they can merge into a single, more massive object that appears younger and bluer than the surrounding stellar population. These blue stragglers stand out like cosmic anachronisms, appearing to have turned back the clock on stellar evolution through the violence of their formation. The dense stellar environment also creates opportunities for the formation of some of the most exotic objects in the universe. Neutron stars, the collapsed cores of massive stars that have undergone supernova explosions, become more common in these regions. Some of these neutron stars are spun up to incredible rotation rates by accreting material from companion stars, becoming millisecond pulsars that sweep beams of radiation across space with clockwork precision. X-ray sources become increasingly common as we move deeper into the bulge, marking the locations where matter falls onto compact objects like neutron stars and black holes. The intense gravitational fields around these objects heat in falling material to temperatures of millions of degrees, causing it to emit high-energy radiation that can be detected by space-based X-ray telescopes. But perhaps most remarkably, we begin to encounter the influence of something far more massive than any individual star or stellar remnant: the central black hole. still thousands of light years away, begins to make its presence felt through the subtle but measurable effects it has on the motions of stars and gas throughout the galactic bulge. This gravitational influence manifests in several ways. The overall rotation curve of the galaxy, the relationship between orbital velocity and distance from the center, shows clear evidence of a central mass concentration. Gas flows in the inner galaxy are channeled by gravitational forces that can only be explained by the presence of a supermassive black hole. And the orbits of individual stars, particularly those closest to the galactic center, show the unmistakable signature of motion in an extremely strong gravitational field. The interstellar medium in the galactic bulge is dramatically different from anything we encountered in the spiral arms. Here, the space between stars is filled with hot ionized gas heated by the collective radiation from millions of evolved stars. Temperatures reach millions of degrees, creating a tenuous but extensive atmosphere of hot plasma that extends throughout the bulge region. This hot gas doesn't just fill space passively, it flows driven by pressure gradients, magnetic fields, and the gravitational pull of the central black hole. Streams of gas fall inward along complex trajectories, sometimes forming temporary ring structures or spiral patterns as they respond to the gravitational forces and magnetic fields that thread through the galactic center. The magnetic environment itself becomes increasingly complex as we approach the galactic center. The magnetic field lines, which in the spiral arms generally follow the spiral structure, become twisted and distorted by the complex motions of gas and the influence of the central black hole. These magnetic fields can channel the flow of cosmic rays, trap hot gas in magnetic loops, and accelerate charged particles to incredible energies. As we continue our inward journey, the very nature of space and time begins to change in subtle but measurable ways. The intense gravitational field of the central black hole, though still distant, creates relativistic effects that become increasingly important. Time runs slightly slower than it would in the galactic suburbs. Light is gravitationally redshifted as it climbs out of the deepening gravitational well, and the paths of particles, whether they're photons of light or cosmic ray nuclei, begin to curve noticeably as they respond to the warp geometry of space-time. The stellar populations around us continue to evolve as we move deeper into the bulge. We encounter more and more stars in advanced stages of evolution, red giants that have swollen to enormous sizes as they exhaust the hydrogen fuel in their cores, white dwarf stars, the hot dense remnants of stars like our Sun that have shed their outer layers and settled into their final cooling phase. And increasingly we find evidence of stellar populations that have been stirred and mixed by the complex gravitational environment. Some regions of the bulge show evidence of more recent star formation, suggesting that the supply of gas for making new stars hasn't been completely exhausted despite the ancient age of most bulge stars. These younger stellar populations create a complex layered structure where stars of different ages and chemical compositions coexist in the same region of space. The dust that we encountered abundantly in the spiral arms becomes increasingly rare as we move deeper into the bulge. The hot ionized gas and intense radiation fields strip away or destroy much of the fine dust that serves as the raw material for planet formation in the outer galaxy. What dust remains tends to be concentrated in dense clouds that have somehow managed to survive in this harsh environment. This scarcity of dust has profound implications for the formation of planetary systems in the galactic bulge. While planets can and do form around bulge stars, they're likely to be primarily gas giants and rocky worlds with very different compositions than the planets in our solar system. The reduced abundance of heavy elements and the scarcity of dust make it less likely that Earth-like worlds could form and maintain stable, habitable conditions. Yet even in this seemingly hostile environment, we find evidence of complex chemistry and molecular formation. Radio telescopes have detected various molecular species in the dense gas clouds of the galactic bulge, including some of the same organic molecules found in star-forming regions throughout the galaxy. The chemistry of life, it seems, can find ways to operate even in the most extreme galactic environments. As our journey carries us ever deeper into the heart of our galaxy, we begin to sense that we're approaching something truly extraordinary. The gravitational field grows stronger with each passing light year. The stellar motions become more extreme, with stars moving at velocities that would carry them completely out of the galaxy if they weren't bound by the intense gravitational field of the central black hole. Radio and X-ray emissions from the galactic center grow stronger, signaling the presence of high-energy processes operating on scales and at intensities that dwarf anything we've encountered so far. We're approaching a region where the normal rules of stellar physics give way to something far more exotic, where matter and energy interact in ways that push the boundaries of our understanding. The supermassive black hole that anchors our galaxy is still ahead of us, but its influence is now unmistakable. We can see it in the orbital motions of nearby stars, in the flow patterns of interstellar gas, and in the high-energy radiation that escapes from the immediate vicinity of the event horizon. We're approaching the most extreme gravitational environment in our galaxy, where the curvature of space-time becomes so severe that it fundamentally alters the nature of reality itself. Before we can reach that ultimate destination, we must traverse the final regions of the galactic bulge, where stellar densities reach their maximum, where the most exotic stellar populations reside, and where the interplay between gravity, magnetism, and high-energy physics creates phenomena that exist nowhere else in the known universe. The center of the Milky Way beckons with mysteries that will challenge everything we think we know about black holes, gravity, and the fundamental nature of space and time. Our journey is approaching its most spectacular and mind-bending phase, where science meets the truly sublime, and where the universe reveals some of its deepest secrets to those brave enough to venture into the heart of our cosmic home. As we penetrate the final layers of the galactic bulge, something extraordinary begins to unfold around us. The stellar environment transforms into something that challenges our most basic understanding of cosmic architecture. Stars that once seemed densely packed now appear almost sparse compared to what lies ahead. We're approaching the nuclear bulge, the innermost region of our galaxy, where stellar densities reach values that would have seemed impossible just a few thousand light-years ago. Here, within a few hundred light-years of the galactic center, we encounter stellar populations so tightly packed that the average distance between stars shrinks to less than a single light-year. If Earth existed in this environment, our night sky would be ablaze with thousands of stars brighter than the full moon, creating a perpetual twilight that would make true darkness impossible. The gravitational interactions between these closely packed stars create a dynamic, ever-changing stellar ballet, where close encounters and orbital perturbations are not rare events, but routine occurrences that constantly reshape the stellar landscape. The stars themselves tell an even more remarkable story. These are not just ancient population 2 stars, but representatives of some of the most extreme stellar evolution pathways in the universe. We encounter massive red supergiants that have swollen to sizes larger than Earth's orbit, their surfaces so cool they glow with a deep crimson light, yet so luminous they outshine entire star clusters. These dying giants are nearing the end of their nuclear burning phases, and their eventual deaths will seed this region with heavy elements and explosive energy. But perhaps even more striking are the stellar remnants that populate this region. White dwarf stars, the compressed cores of dead solar mass stars, are scattered throughout the nuclear bulge like cosmic diamonds. Each white dwarf represents the final fate of a star that once burned hydrogen in its core for billions of years before exhausting its fuel and shedding its outer layers into space. These remnants are incredibly dense, containing roughly the mass of our Sun compressed into a sphere the size of Earth, creating gravitational fields so intense that a teaspoon of white dwarf material would weigh as much as a car. Even more exotic are the neutron stars that occasionally reveal themselves through their emissions. These objects represent the collapsed cores of massive stars that died in supernova explosions. Their protons and electrons crushed together by gravity to form neutrons in a state of matter so dense that a sugar cube-sized piece would weigh as much as a mountain. Some of these neutron stars have been spun up to rotation rates of hundreds of times per second by accreting material from companion stars, becoming cosmic lighthouses that sweep beams of radiation across space with metronomic precision. The interstellar medium in this region has been transformed by eons of stellar evolution and death. The space between stars is no longer the cold, relatively empty void we encountered in the spiral arms, but a hot, turbulent ocean of ionized gas heated to temperatures of millions of degrees by countless stellar winds, supernova explosions, and the intense radiation field created by the dense stellar population. This hot gas doesn't remain static, but flows in complex patterns driven by pressure gradients, magnetic forces, and the overwhelming gravitational pull of the central black hole. Magnetic fields thread through this environment with an intensity and complexity that dwarfs anything found in the outer galaxy. These fields are generated by the collective motions of the hot, ionized gas and are continually twisted and amplified by the differential rotation of the galactic center. The resulting magnetic structures can channel the flow of cosmic rays, accelerate charged particles to relativistic speeds, and create phenomena that bridge the gap between stellar physics and high-energy particle physics. As we continue our inward journey, we begin to encounter evidence of truly extraordinary events. Hypervelocity stars, massive objects moving at speeds of thousands of kilometers per second, occasionally streak through this region on trajectories that will carry them completely out of the galaxy. These cosmic cannonballs were likely accelerated by close gravitational encounters with the central supermassive black hole. Slingshot effects so violent they can eject entire solar systems from the galactic gravitational well. The chemistry of this region reflects its extreme environment. While complex molecules are rare due to the intense radiation fields and high temperatures, we do find evidence of unusual chemical processes driven by the extreme conditions. High-energy cosmic rays create exotic isotopes through nuclear reactions that occur nowhere else in the galaxy. The intense magnetic fields can affect the behavior of atoms and molecules in ways that are only beginning to be understood by theoretical physicists. Radio observations reveal structures that hint at the complex dynamics operating in this region. Filaments of hot gas stretch across dozens of light years, aligned with magnetic field lines, and glowing with synchrotron radiation as relativistic electrons spiral through the magnetic field. These structures suggest that the galactic center is not just a passive gravitational sink, but an active, dynamic region where matter and energy interact in ways that create phenomena visible across the electromagnetic spectrum. X-ray emissions become increasingly prominent as we approach the very center of our galaxy. These high-energy photons are produced by a variety of processes, from the accretion of material onto compact objects, to the shock heating of gas as it falls inward toward the central black hole. The X-ray glow creates a kind of high-energy aurora that would be invisible to human eyes, but reveals the presence of physical processes operating at temperatures and energies that exceed anything found in normal stellar environments. Perhaps most remarkably, we begin to detect the influence of general relativistic effects that are negligible in the outer regions of the galaxy. The intense gravitational field of the central black hole starts to measurably affect the propagation of light, the flow of time, and the geometry of space itself. Photons climbing out of the gravitational well lose energy and become redshifted. Clocks would run measurably slower than they do in our home solar system, and the paths of particles, whether they're cosmic rays or streams of gas, begin to curve in ways that can only be explained by Einstein's theory of general relativity. The stellar orbits in this region provide some of the most direct evidence for the presence of the supermassive black hole. Stars that venture close to the galactic center follow highly elliptical orbits that carry them at tremendous speeds through their closest approach. Some of these stars reach velocities of several percent the speed of light during their closest approach to the black hole, creating natural laboratories for testing general relativity under extreme conditions. These orbital motions also reveal the incredible precision of celestial mechanics operating under extreme gravitational conditions. Stars that complete their orbits in just a few decades provide astronomers with the opportunity to watch general relativistic effects in real time. The precession of elliptical orbits, the gravitational redshift of starlight, and the time dilation effects on stellar clocks all become measurable phenomena that confirm our understanding of gravity under conditions that cannot be replicated in any terrestrial laboratory. The dust that managed to survive the harsh environment of the outer galactic bulge becomes virtually non-existent in this innermost region. The intense radiation fields, hot gas, and stellar winds strip away or destroy virtually all solid particles, leaving behind a medium that is almost purely gaseous. This absence of dust has profound implications for the types of astronomical observations that are possible from this region. and for any hypothetical planetary systems that might exist around the surviving stars. Yet, even in this seemingly sterile environment, we find evidence of ongoing star formation, though of a very different character than what occurs in the spiral arms. Dense molecular clouds occasionally form from the cooling of hot gas in the shadows of massive stellar winds, or in regions where magnetic fields provide some protection from the intense radiation. When these clouds reach sufficient density, they can collapse to form new stars, creating small populations of young massive stars in an otherwise ancient stellar environment. These young stars burn bright and hot, their intense stellar winds and eventual supernova explosions adding even more energy to an already extreme environment. Their formation represents a kind of galactic recycling, where material from ancient stellar populations is reprocessed and reformed into new generations of stars that will burn briefly but brilliantly before adding their own contributions to the complex chemical and energetic environment of the galactic center. The gravitational environments become so extreme that we begin to encounter phenomena that exist nowhere else in the known universe. Tidal forces from the central black hole can disrupt stellar systems, strip material from the surfaces of close approaching stars, and create streams of gas that spiral inward along complex trajectories. These tidal effects operate on scales from individual atoms to entire stellar systems, creating a hierarchical structure of gravitational influence that extends outward from the event horizon of the central black hole. As we approach the final phase of our journey, the very nature of space and time continues to change in ways that would be imperceptible to our senses, but measurable by our most sensitive instruments. The metric of space-time itself becomes curved by the intense gravitational field, creating a geometry where parallel lines converge, where the shortest distance between 2 points is no longer a straight line, and where the familiar Euclidean geometry of everyday experience gives way to the non-intuitive mathematics of curved space-time. The event horizon of Sagittarius AA, our destination, begins to exert its influence even from distances of several light years. This is not a physical boundary that we could touch or see, but rather a mathematical surface defined by the point of no return, the distance from the black hole where the escape velocity equals the speed of light. Beyond this boundary, not even light can escape the gravitational pull of the black hole, creating a region of space that is fundamentally disconnected from the rest of the universe. But approaching this boundary reveals phenomena that push the boundaries of physics itself. The intense gravitational field creates conditions where quantum effects become important on macroscopic scales, where the vacuum of space itself becomes unstable, and where the familiar distinction between matter and energy begins to break down. Virtual particle pairs can be separated by tidal forces, with one member falling into the black hole while the other escapes as Hawking radiation, creating a slow but steady evaporation process that connects the quantum world to the macroscopic realm of general relativity. The magnetic fields in the immediate vicinity of the black hole reach strengths that dwarf anything found elsewhere in the galaxy. These fields are generated by the motion of ionized material as it spirals inward toward the event horizon, creating a magnetosphere around the black hole that can accelerate particles to energies comparable to the most powerful particle accelerators ever built by human civilization. The interaction between these magnetic fields and the rotating black hole may power some of the most energetic phenomena in the universe, from relativistic jets that can extend for thousands of light years to the high-energy emissions that make active galactic nuclei visible across cosmological distances. As we prepare for the final approach to Sagittarius AI, we find ourselves at the threshold of a realm where the normal rules of physics are stretched to their absolute limits. Here, in the heart of our galaxy, we encounter conditions so extreme that they serve as natural laboratories for testing our most fundamental theories about the nature of reality itself. The journey that began in the quiet suburbs of our solar system has brought us to a place where space and time themselves become active participants in the cosmic drama, where matter and energy interact in ways that challenge our deepest understanding of how the universe works. The supermassive black hole that anchors our galaxy awaits us, a gravitational monster containing the mass of over 4 million suns compressed into a region smaller than our solar system. It is simultaneously the most destructive and the most creative force in our galaxy, capable of tearing apart anything that ventures too close, while also serving as the gravitational anchor that holds our entire galactic home together. In just a few more moments of our cosmic journey, we will encounter this ultimate expression of gravity's power and witness phenomena that exist at the very edge of what physics tells us is possible in our universe. The final approach to Sagittarius AI unfolds like a descent through the layers of reality itself. As we drift closer to this gravitational leviathan, the very fabric of existence begins to reveal secrets that have remained hidden since the birth of our galaxy. The space around us, once filled with the familiar glow of distant stars, transforms into something far more alien and magnificent. Here, within just a few light years of the event horizon, we encounter what astronomers call the S-star cluster. These are some of the most remarkable stellar objects in our galaxy, massive stars caught in the gravitational embrace of the black hole, following orbits so extreme they challenge everything we thought we knew about stellar dynamics. Some of these stars complete their elliptical journeys around the black hole in periods measured in decades, rather than the millions of years typical of galactic orbits. CES2, perhaps the most famous of these captive suns, follows an orbit so eccentric that it approaches within just 120 astronomical units of the black hole at its closest point. That's closer than Pluto orbits our Sun. Yet, this massive star survives its harrowing journey around a gravitational field 4 million times more intense than our Sun's. At periapsis, S2 reaches velocities of nearly 30 million km/h, moving at almost 3% the speed of light, as it whips around the black hole in a cosmic dance that lasts just 16 years. These stellar orbits provide us with the most direct evidence for the existence of Sagittarius A*, and offer unprecedented opportunities to observe general relativistic effects in action. As S2 approaches its closest point to the black hole, its light becomes measurably redshifted by the intense gravitational field. Time dilation effects become so pronounced that clocks on the star would run noticeably slower than identical clocks in our solar system. The precession of the orbital ellipse, predicted by Einstein's field equations, becomes observable over just a few orbital periods. But perhaps most remarkably, these observations allow us to probe the structure of space-time itself in the immediate vicinity of a black hole. The motion of stars like S2 maps out the curvature of space in real time, revealing how mass and energy warp the geometry of the universe. It's like watching the mathematical abstractions of general relativity play out in the movements of actual stars, turning theoretical physics into observable astronomical phenomena. The accretion disks surrounding Sagittarius AA create one of the most extreme physical environments in the known universe. Here, matter spirals inward along trajectories that carry it ever closer to the point of no return, heating up through friction and magnetic interactions until it glows with temperatures exceeding 100 million degrees Kelvin. This is matter in its most extreme state, a plasma so hot that atoms are completely ionized, electrons stripped away from their nuclei and moving at relativistic speeds. As this superheated material approaches the event horizon, it doesn't simply disappear quietly into the black hole. Instead, it creates a brilliant display of high-energy physics that can be observed across the electromagnetic spectrum. X-rays and gamma rays pour out of the accretion disk as magnetic field lines twist and reconnect, accelerating particles to enormous energies and creating shock waves that propagate through the surrounding medium. The magnetic field structure around the black hole itself represents one of the most complex and powerful magnetic environments in the galaxy. These fields are generated by the motion of the ionized accretion disk and are continually wound up and amplified by the rotation of the black hole itself. The resulting magnetic field lines can become so twisted and energetic that they occasionally snap and reconnect, releasing bursts of energy that can illuminate the entire galactic center region. Some theoretical models suggest that these magnetic fields may be responsible for launching relativistic jets from the vicinity of the black hole. These jets, streams of particles accelerated to nearly the speed of light, can extend for thousands of light years beyond the black hole itself, carrying energy and momentum far out into the galaxy. While Sagittarius A appears to be relatively quiet compared to the supermassive black holes in more active galaxies, there is evidence that it may have been much more active in the past, possibly launching powerful jets that helped shape the structure of the galactic center region. The immediate environment around the black hole is also populated by a zoo of exotic objects and phenomena that exist nowhere else in the galaxy. Neutron stars, those incredibly dense stellar remnants, can survive surprisingly close to the black hole. Their strong magnetic fields and rapid rotation create pulsars that sweep beams of radiation through the galactic center. Some of these pulsars have been accelerated to incredible velocities by gravitational interactions with the black hole, creating natural particle accelerators that achieve energies comparable to the most powerful machines built by human civilization. Perhaps even more exotic are the theoretical objects that might exist in this extreme gravitational environment. Strange matter, composed of quarks arranged in configurations that don't exist under normal conditions, might form in the crushing gravitational fields near the event horizon. Primordial black holes, remnants from the early universe that somehow survived to the present day, might be captured by Sagittarius A and slowly consumed, adding their mass to the central object while releasing distinctive gravitational wave signatures. The space immediately surrounding the black hole is also where our understanding of physics approaches its limits. Here, quantum effects that are negligible under normal conditions become important on macroscopic scales. The intense gravitational field creates conditions where virtual particle pairs can be separated by tidal forces, leading to the Hawking radiation process that causes black holes to slowly evaporate over cosmological timescales. Near the event horizon, the distinction between space and time becomes blurred in ways that challenge our everyday understanding of reality. To an outside observer, time appears to slow down dramatically for objects approaching the black hole, with clocks running slower and slower until they appear to freeze completely at the event horizon. Light from these objects becomes increasingly redshifted, fading to invisibility as the photons lose energy, climbing out of the deepening gravitational well. Yet from the perspective of matter falling into the black hole, the journey continues normally. The falling observer experiences no slowing of their local clocks, no sense that anything unusual is happening, until they encounter the increasingly strong tidal forces that ultimately stretch and compress matter in the final approach to the singularity. This fundamental difference in perspective, where the same events appear completely different to different observers, illustrates one of the most profound aspects of general relativity. The event horizon itself represents a boundary, unlike anything else in physics. It's not a physical surface that could be touched or seen, but rather a mathematical boundary, defined by the condition that the escape velocity equals the speed of light. Once matter crosses this boundary, it becomes causally disconnected from the rest of the universe. No information, no signal, no influence of any kind can propagate back across the event horizon to affect events in the external universe.